So, good morning, everyone. My name is José Ferreira. I'm a master's student at the Faculty of Sciences of the University of Lisbon and at the Institute of Astrophysics and Space Science. And today I'm here to talk to you about forecasting FFQ cosmology with a lambda CDM background using standard Sirens, which has been developed with José Mimoso, Nelson Nunes, and Tiago Barreiro, and is based on the following archive ID. Okay, so here's the outline for the presentation. I'm going to start by introducing the cosmological model that we have considered. First, due to recent theoretical developments, we've considered a symmetric teleparallel gravity model, where gravity is ascribed to a flat, torsion-free, and metric spacetime. We also assume a flat and homogeneous and isotropic universe, which is given by the FLR-2 metric. And then one can show, under these assumptions, that the most general function that recovers the lambda CDM background, which can be derived directly from the first modified Friedmann equation, is the following. Knowing that f of q equals to q, we have what is known as the symmetric teleparallel equivalent to general relativity. That is a metric theory which is in everything equivalent to GR. We can see that this model is quite simple, as it only adds one additional free parameter, m, which falls back to general relativity if set to 0. This model has also been shown to alleviate the sigma 8 tension in previous works. As such, this is the model that we have considered throughout this work. Additionally, we have considered a universe which is made up of ordinary and dark matter, as well as dark energy. So we've neglected the radiation, which is fine because we're considering black hole formations and star and siren events. Using conservation laws, we can express omega lambda as a function of omega m. And this results in the following Hubble function, which is exactly the same for lambda CDM as intended. So if the background is the same, what changes? By introducing a function f of q in the action, we obtain what is known as an effective gravitational constant, which is given generically by the following form, where the index q stands for a derivative in respect to q, which is the non-metricity scalar introduced before. This in turn modifies the luminosity distance for gravitational waves with the following multiplicative term. In our model, we can see that the luminosity distance for gravitational waves is given by the following expression, where here the L of C, as well as here, is the standard luminosity distance in a lambda CDM model. We have considered here that m is to be in the units of 1/h0, and also that E of z is the Hubble function without the Hubble constant. This difference right here will be the key in telling this model from lambda CDM apart. Okay, so now that we know the cosmological model that we have considered, let's talk about the data sets that we've been using. So it's standard Sirens and type 1a supernova. First, let's start with standard Sirens. Unfortunately, there's only been one standard Siren event so far, which is not even close enough to constrain this model. As such, we have to consider mock catalogs of standard Siren events. In the slides, I will outline the procedure that we have employed to generate such catalogs. We start off with the theoretical probability distribution function as a function of redshift for standard Siren events, which we then sample to obtain a given redshift, which we represent with the point mark in red, schematically. We then compute the corresponding luminosity distance using some reference cosmology, which in our case, we took it to be some lambda CDM, but this can be adjusted. We then consider the error as a function of the redshift, compute the corresponding error for that observatory for the redshift that we have previously obtained, and then consider it to be the 1 sigma region and down around the computed value for the luminosity distance. Because in real life, the most likely value doesn't fall on top of the expected value, we decided to sample a Gaussian distribution to distribute these points around using around the most likely value, or the theoretical value, sorry, by considering the median equal to the point in red and the standard deviation equal to the error bar in blue. To automate this procedure, we have created a small tool, which is written in Python, which we have called GW Catalog, that can be easily installed, modified, and extended if, for example, you wish to change any of the underlying distributions, or you want to add other observatories. We then repeat this process equal to the number of times, equal to the number of events we expect to observe, and equal to the number of observatories that we are considering. And so, which observatories have we considered in our analysis? We have LIGO, LISA, and the Einstein telescope, all of which are forecast naturally, and I imagine that you're almost familiar with each of them. Okay, so I also mentioned that we're using type 1a supernova. Why are we using type 1a supernova? Because if you remember the luminosity distance for gravitational waves, we have the following multiplicative term. This term right here, where E of c implicitly depends on omega matter, introduces a degeneracy between m and omega matter. To avoid problems in our sampler, we decided to fix the omega matter with type 1a supernova. Okay, so now that we know the cosmological model and the datasets, let's see how we're joining the two together in the next section. Okay. So because we're talking about catalogs and statistical distributions, we need to provide confidence that our results do in fact make sense. As such, we have generated 15 different catalogs for LISA, each with 15 events, which is the expected number of events for a 4-year mission lifetime, and pick the best, median, and worst catalogs. For us to say what the best, median, and worst catalog is, we rated them based on how small the 1 sigma region is for the parameter m. For the Einstein telescope, we generated 5 different catalogs, each with 1,000 events, which is also, if I'm not mistaken, the expected number of events they expect to observe for a 3 to 4 year mission lifetime, which also showed to be very similar, so we only had to consider 1 catalog. For LIGO, on the other hand, we generated 15 catalogs, each with 50 events. However, LIGO alone wasn't able to set proper forecasts on our model. As such, we have to consider the best, median, and worst catalog based on how well it would complement the worst LISA catalog. As for the sampling, very briefly, we have used the Gaussian likelihood for the luminosity distance for gravitational waves. As for type 1a supernova, as I mentioned before, we have performed some marginalizations such that it only fixes the value of omg, so it doesn't depend on anything else, it doesn't fix anything else. And for our sampler, we have used STEN, which is a sampler written in C++, which implements the no U-turn sampler, which is a variant of the Hamiltonian Monte Carlo method, which can be used across different programming language, where this was the parameters for each run. Okay, so what results have we obtained in our analysis? First, let's start things off with LISA. On the left, you can see the catalogs, and on the right, you can see the constraints. You can see that the worst LISA constraint, the worst LISA forecast is significantly worse than the median, which is in pink, and the best, which is in blue. The orange is in, the worst is in orange. By contrast, the median and the best catalog are very similar to each other. If you look in the left and you analyze this plot in due time, you can actually see a pattern. So the best LISA catalog seems to be the one that features more low redshift events, while the worst LISA catalog seems to be the one that features more high redshift events, so less low redshift events. And the median is somewhere in between. So this makes us believe that there's an optimal region in low redshifts to constrain this model. As for the Einstein telescope, as I said before, we only consider 1 catalog with 1,000 events. As you can see, that's a lot of events, which is a number of events large enough to closely match the underlying statistical distribution. That's the reason why we only had to consider 1 catalog. If we compare the best LISA catalog with the single Einstein telescope catalog, you can see that the Einstein telescope catalog is slightly better than the one set by LISA. Interestingly, you can see that LISA spreads across a much wider range of redshifts. Yet, the Einstein telescope is able to give better constraints, which means that studying high redshift events is not a requirement to forecast this model. Granted, the number of events set by the Einstein, measured by the Einstein telescope is much larger, so we're comparing 1,000 events to 50 events. But it's still interesting to see that this result holds, and the fact that 50 events by LISA are actually comparable to 1,000 events set by the Einstein telescope. As for LIGO, as we mentioned before, it's not able to proper forecast this model by itself, so we had to add the worst LISA catalog to the mixture. As you can see, the worst LISA catalog by itself, which is in orange, has some improvements when we add the LIGO catalogs that we have obtained in the mixture, both the best, median, and worst. This means that if in the future we are unlucky enough to obtain a bad LISA catalog, which we believe to be quite unlikely, we can still use the data from LIGO to improve those results and approximate it to a median LISA catalog. So we don't lose much if we happen to have a worse LISA catalog, which is good news. So we wanted to understand why isn't LIGO itself able to constrain this model. So what we did was zoom in the low redshift regime and compare the best LISA catalog with the best LIGO catalog and the single Einstein telescope catalog. And what we saw is that the error bars from LIGO, which are in blue, are just massive when compared to the Einstein telescope, which is in pink. And the error bars from LISA, which is in orange, aren't even visible at the scale. So this is the reason why LIGO itself isn't able to properly forecast our model, even though it's in the low redshift regime where we believe that both LISA and Einstein telescope perform best, because the error bars are simply huge. This also explains why 15 events set by LISA can actually compare against 1,000 events by the Einstein telescope, because the error bars from LISA are just so small. Okay, and here we can see the corresponding constraints, which again are more or less the same. Then, as a final step, we decided to see what happened when we add the Einstein telescope and LISA together. And we can see that there's only slight improvements when we consider the best LISA catalog. So nothing significant here. And surprisingly, when we do the same analysis with LIGO, nothing happens because LIGO itself isn't able to add anything to the already optimal constraints that the Einstein telescope sets. Okay, so let's wrap up this presentation with a few closing thoughts. As for our results, we showed that the Einstein telescope showed to perform better than LISA. LISA showed to perform better than LIGO, and LIGO alone will not be able to constrain this model. We obtained different catalogs for LISA and LIGO, which are explained by the significant, by the decreased number of events when compared to the Einstein telescope, but not for the Einstein telescope. And if we happen to obtain a LISA catalog, we can use LIGO to complement it and obtain better constraints to approximate it to a median LISA catalog. We also show in a complementary analysis, which is not shown here for brevity, that the optimal region for in redshift range for LISA is approximately 0.6 and approximately 0.1 for the Einstein telescope. I should reinforce that even though all of this is forecasting, the machinery that we have developed here can be used when such data is available to actually provide constraints on any given model. It can also be used to test other models of modified gravity, not necessarily this one, which introduce a modification to the luminosity distance of gravitational waves, which is something that we're doing at the moment. Okay, so thank you for your attention, and I'm open to questions.
Okay, one comment. These are standard science in the sense that you are assuming to know the redshift from an electron. Okay, then for Einstein telescope, 1,000 events are too much.
We also believe that it was too much, but it was in the paper that we considered. Hang on, let me just check. So for the Einstein, according to this paper right here, I don't remember which one is it by heart, but they said that they were going to measure 1,000 Einstein telescope events, and we believe them. That's all I can say about it.
Which telescope it is? I mean, how they assume to take the content? Because, for example, if you take the
I'm sorry, can you say that again?
If you take as a next generation mission Theseus, which will be an X-ray, we should be, if it will be accepted, an X-ray satellite, okay, detecting the gamma ray burst and then detecting gravitational wave. They assume to, well, they forecast to detect around 1 to 107 Fouriers. That's it. This is why I was saying that there's not too much.
Okay. And
another thing is you say that in the beginning you say that you fix omega m to the value of the you get from supernova, right?
Yeah, correct.
But in what sense? As a prior or in sense that you fix? Because at the end you also fit omega m.
No, we just add the data set. So we're just adding those standard sirens, and then we add the type 1A supernova on top.
In that sense.
Yes, that's why the constraints, if you can, it's refusing to collaborate. Okay, that's why the constraints always have the same omega matter. So that's they always agree on the value of omega matter, because we're using type 1A supernova to fix it, but not as a prior. We're just adding the data, and the sampler is telling us that.
Okay, thank you.
So we can continue the discussion in Slack. So there was another question, but or not? Yeah, please continue in Slack because we have to go to the next.